Today, we are going to start trigonometry.
Okay.
Alright? So, what we did yesterday, with rationalizing denominators, simplifying radicals, is something we will need to do this. Okay, so when we start actually doing trig problems, we will be using the idea that we talked about yesterday. So, once we get to a point where we're just practicing some problems today, I'm going to come around and check that sheet from yesterday just for a completion grade. Alright? So, intro to trig. Trigonometry is just the study of the relation between the sides and angles of a triangle. Specifically, what we're going to look at to start here is just right triangles. Okay, I haven't decided if we will have time to look at using trig to solve any triangle yet or not. Right? So that we are just going to be working with right triangles to start. Now, there are actually 6 trig functions. Right? There are actually 6 of them. You've only seen 3 of them before, and we're only going to focus on 3 of them today. Okay, but we will look at all 6 of them eventually. The 3 that you have seen before are sine, cosine, and tangents. Okay, you've seen those in your geometry class. Now, the way that we abbreviate these are sin, cos, and tan. Okay, now, so when we see this, this isn't sin, this isn't cos, this isn't tan. We would still say sine, cosine, and tangent. Okay, this is just the way that we abbreviate it. Right, so when you see cos, you would still say cosine. Right? You would still say tangent. You would still say sine. Right? So to use these trig functions, we need to make sure that we understand a few vocab ideas. What's that?
Water boy? Water boy?
Yeah.
Taxing fuel?
Sorry, tactical fuel. Alright. The first is theta. Does anybody know what theta is?
No.
Yeah. Theta is just a Greek letter. Right?
Whoa!
Theta is just a Greek letter that looks like this.
There's a 0. Circle of
Yeah, it's just yeah, I mean,
well, it's a little
because,
bit.
yeah, it goes all the way through. I just didn't connect it there. Right? So theta is a Greek letter that looks like this. Letter. It's a letter. So what we use theta for is just a variable. It's just kind of tradition to use Greek letters as variables for angles. Okay? So we'll say this is a variable for an angle. Okay? So you would think of it just as an x, right? This is just a variable. Right? But generally we use Greek letters, specifically theta, for a variable for an angle. Right? Now, when we are looking at a triangle, right, the first thing we are going to do in any trig problem that we ever do is label the 3 sides as opposite, adjacent, and hypotenuse. So the opposite side, right, in a triangle is going to be the leg that is not touching the given angle. What do I mean when I say leg? What's a leg in a right triangle? Right. Yeah. The legs are the 2 sides that make up the right angle. So we're saying the leg, which is one of the sides that makes up the right angle, that is not touching the given angle. Okay. Then the adjacent side is the leg that is touching the given angle. Then how would I describe what the hypotenuse is?
The one that isn't gross.
It is always the longest side, and it is the one that isn't those, right? So, I mean, we could say it's the longest side, or we could say the side that is opposite the right angle, the one that's not touching the right angle. All right, the side opposite the right angle. So, before we even define our trig functions, let's make sure that we understand how to label the triangle like this. Labeling the opposite side, the adjacent side, and the hypotenuse. So, your next two examples underneath, okay, we just have two triangles. And we've got theta in different places. Okay? Up here, or in my first example, my theta is in my top angle. In the second triangle, my theta is in the bottom right. So, what I want to do is label the three sides, opposite, adjacent, and hypotenuse, with respect to this angle. So if I'm saying this is my given angle, this is where theta is, which side, this one, or this one, is opposite the very bottom. Okay? So we'll say this is opposite. Now which side would be adjacent? The one on the left. How do I know what the difference is between these two? Yeah, I mean that's one way to look at it, right? The hypotenuse might be the easiest one to find, right? Because that's the one that's going to be opposite the right angle. Right? So once we find the hypotenuse, the opposite one is not touching the given angle. The adjacent one then is the leg that is touching the given angle. Now, on my second triangle here, I put my theta down in the bottom right. What does that change? Exactly. It changes the opposite and the adjacent. The hypotenuse does not change. Right? The hypotenuse is still the side that's opposite the right angle. But the opposite side is over here. And the adjacent side would be down here. Right? So, let's go ahead and define our trig functions now. The way that we are going to define our sine function is just the ratio of the opposite side over the hypotenuse. The way that we are going to define our cosine function is just the adjacent side over the hypotenuse. And the way we are going to define tangent is the opposite side over the adjacent side. Now, the trick to remembering these, right, no matter where you took geometry, no matter who you had, you've seen this little remembering device. SOHCAHTOA. Right? SOHCAHTOA. So I'm going to scroll up a little bit and rewrite this here. So I can fill in what this means. Okay, so we get TOA, right? This stands for sine is opposite over hypotenuse. This stands for cosine is adjacent over hypotenuse. Adjacent over hypotenuse. This stands for tangent is opposite over adjacent. Right? That's what we just wrote in the line above. So let's then take a look at our first example problem and figure out what this all actually means. Right? Whenever I've got a triangle, the first thing I want to do is label the three sides, opposite, adjacent, and hypotenuse. So with respect to this angle, which is the opposite side, the 3, 4, or 5? 3. And this would be the opposite side, the one that's not touching that angle, which would be the adjacent side. 4. Then the hypotenuse would be 5. So, all we're going to do today is write out our trig ratios. Right? So I want to find the sine of theta, the cosine of theta, and the tangent of theta. So using my definition of what sine is just the opposite side over the hypotenuse. So here, sine would be 3 over 5, opposite side over the hypotenuse. So using that definition, what would cosine be? 4 over 5, right? Cosine is the adjacent side over the hypotenuse. What would my tangent be here? Tangent would be 3 over 4. Okay? So sine is just the ratio of the opposite over the hypotenuse. Cosine is the adjacent over the hypotenuse. And tangent is opposite over adjacent. Okay. Questions so far? Yes. So I want you guys then to go ahead and flip over and try 1, 2, and 3. Okay, try 1, 2, and 3. Now, when we have our ratios, these are just fractions, right? We always want to reduce if possible. And we can't have square roots in the denominator, just like what we worked on yesterday. Okay, so on some of these problems, we will end up with square roots in the denominator. So, sometimes in our answers we need to reduce, sometimes we need to rationalize, meaning get rid of square roots in the denominator. Okay, so go ahead and flip over and try numbers 1, 2, and 3. Okay, find the sine, cosine, and tangent of the given angle for those problems. All right, and as you are working on those, go ahead and have out your... Alright, so as I was walking around, it looked like most people were good on 1 and 2. The only potential thing I saw on number 1, I saw some people not reduce. Okay, like you should have had 6 over 10, 8 over 10, and 6 over 8, I believe, for your 3 trig functions. Yeah. Those all reduce. Right? All 3 of those fractions would reduce. So make sure that you are checking to see if they reduce. Right? Now, on number 3, okay, this is where it might have gotten a little bit trickier. Now, the first thing that we want to do is still label the sides, opposite, adjacent, and hypotenuse. So for number 3, I should have labeled my triangle like this, opposite, adjacent, and hypotenuse. Then to write my trig functions, sine of theta, well, sine we said is opposite over hypotenuse. So 2 over 8. Does that reduce? 1 over 4. Right? So 1 over 4 would be my answer. No, I don't have to get rid of the 2 over 8 or erase it or anything. I can just write it like this, right? My unsimplified version, and then say that's equal to 1 over 4. Then cosine. So cosine of theta is adjacent over hypotenuse. So adjacent over hypotenuse, I'm just going to write exactly how I see 2 radical 15 over 8. I don't have a square root in the denominator, so we're good there. Right? I only have to worry about rationalizing if the square root is in the denominator. Okay? It's not, so we don't have to mess with that. But we do want to see if this part will reduce. Well, I've got 2 over 8 again, just like I did in my first problem. Right? So that would just reduce to 1 times the square root of 15 over 4. Now, I don't have to write that 1. Right? It's not wrong if you do, okay? But to make it look a little bit cleaner, I don't have to write that 1. Right? I can just write it as the square root of 15 over 4. Now my last one here, tangent of theta. So tangent is opposite over adjacent. Right? So I would have 2 over 2 times the square root of 15. Here, I do have a square root in the denominator. It's no good, right? I can't have that for a final answer. So we have to practice or use what we did yesterday. So what do I need to do to get rid of that square root in the denominator? Multiply top and bottom by the square root of 15. So, in my numerator, this 2 is on the outside of the radical, the 15 is on the inside, so I can't really do much with that. I'll just write that as 2 times the square root of 15. But in the denominator, that 2 will still be there, and then I can multiply the 15s together since they're inside of the radical. So that would be square root of 225. Well, now I can take the square root of 225. Right? That should be a perfect square. So this just becomes 15. Okay, the square root of 225 is 15. And remember, when you actually take the square root, the radical, the square root symbol goes away. So now we've got 2 times the square root of 15 over 2 times 15. I can do that now since this is no longer inside of the square root. That's just 30. And then we want to see if we can simplify what we have left. So 2 over 30. Well, those are both divisible by 2. Right? So that would just reduce to 1 over 15. So 1 times the square root of 15 over 15. And remember again, if I'm multiplying 1 times something, we don't have to write that 1. Okay? It's not wrong if you do, but to just make it look a little bit nicer, we can get rid of that 1. Okay, you okay with that one? Yeah. Alright. Something similar would happen in number 4. We would have to rationalize 2 of the denominators, right, for both sine and cosine. So if we write this one out, sine of theta. Actually, I guess I should need to label my triangle first. Right? We didn't do that. This would be the opposite. This would be the adjacent. This would be the hypotenuse. So now, once we label, then I can say sine is opposite over hypotenuse. So that would be 4 over 13 times the square root of 5. That's not a good answer yet. Okay? I can't have a square root in the denominator. So I would need to multiply both the top and the bottom by the square root of 5. Yep. We're on number 4. So again, in the numerator, can't really do much with those. That would just be 4 times the square root of 5. In the denominator, then, I can multiply what's inside the radicals together to get the square root of 25. So then we've got 4 times the square root of 5 over 13 times 5, which is just 65, right? Okay. Then we want to check to see if 4 over 65 would reduce. It doesn't, right? So this would be our final answer. 4 times the square root of 5 over 65. And you can double check yourself, right? You can put this original thing into the calculator. 4 divided by 13 times the square root of 5. And then you can put this one in, 4 times the square root of 5 divided by 65, and see if they're equal. Right? That's a way to double check yourself. Something similar would happen if I do the cosine. Cosine would be adjacent over hypotenuse. So 7 over 13 times the square root of 5. So again, I would need to multiply by the square root of 5 over the square root of 5. So are we starting to recognize a pattern here? The square root of 5 times the square root of 5 is just going to be square root of 25, which is 5. Whenever I multiply a square root times the square root of itself, I'm just going to get that number every single time, right? That's the whole reason that we're doing this. Okay, so if you recognize that, you can give yourself a little bit of a shortcut and say, instead of writing out the step where this is the square root of 25 and then that equals 5, I know that that's just going to equal 5. Right? If I'm multiplying 2 square roots of the same number together, I'm just going to get that number. If that confuses you, don't worry about that. Don't try to do that. Just go ahead and write out the square root of 25 and then that equals 5. Okay, that's perfectly fine. But you can save yourself a step using that idea. Okay. Then my last one, tangent, ends up being a lot easier here. So tangent of theta is opposite over adjacent, 4 over 7, and we're done. Right? There's nothing I can do to simplify that. It's not that.
You see that?
So any questions so far? All right, then let's take a look at the last two problems here, 5 and 6. So on both 5 and 6, we are only given two sides. We are only given two sides. How do I find the third side of a right triangle?
Pythagorean theorem.
Pythagorean theorem. Okay? The Pythagorean theorem. I need to use the Pythagorean theorem to find this missing side before we can write out our three trig ratios. So, yeah, let's call this one x. Now, if we're thinking about the Pythagorean theorem, which two sides are A and B and which side is C?
A.
4 is C, and then these two sides are A and B. Right? And it does not matter which one's A and B, just as long as the hypotenuse is C. So, A squared plus B squared equals C squared. So we've got the square root of 7 squared plus x squared equals 4 squared.
Yep.
What's the square root of 7 squared? 7. Right? So we have 7 plus x squared equals 16. Subtract 7, subtract 7. So, right, then I would have to take the square root, and we get that x is equal to 3. So this side now, I'm just going to erase my x and write 3. Okay. This side now, we know is 3. And then I can do what I did on my last 3 problems, or last 4 problems. Okay, I can write out my sine, cosine, and tangent now. So the first thing I want to do is label the side. So with respect to this angle, 3 is the opposite side. The 7, the square root of 7 is the adjacent side, and the 4 is the hypotenuse. So I can write out my sine. Sine of theta will be opposite over hypotenuse. So 3 over 4. Does that reduce? Nope. There's no radicals. We're done with that one. Cosine of theta. Adjacent over hypotenuse. So square root of 7 over 4. I've got a square root. Do I have to mess with that? Why not? It's on top, right? It's in the numerator. So that's an acceptable answer. There's nothing else to simplify. We're good. We're done with that. And the last one, tangent of theta is opposite over adjacent. So 3 over the square root of 7. What do I do with that one? Is that one an acceptable answer? It's just, yeah. No, not quite. What do I need to do? Divide both the numerator and denominator by the square root of 7. So I'll get 3 times the square root of 7 over the square root of 49. And what's the square root of 49? Just 7. So we get 3 times the square root of 7 over 7. Alright? You guys try number 6. You got 5 minutes left. That's plenty of time.
I tried it.
Okay? Let's try number 6.
Yeah.
So when you get all the way down to the end and you don't get a perfect square, instead of writing it as a decimal, just leave it as a radical. Okay, like this was just left as the square root of 7. Some of the other problems had 2 times the square root of 15. Instead of getting a decimal for that missing side, leave it as a square root.